Now I'm going to go through a few topics that are usually included into the course in ordinary differential equations, but I consciously did not include them. But it is still a good idea to have some very, very basic intuition, some very, very basic understanding. Right? Recall that we've learned how to solve a second order linear differential equation with constant coefficients. Homogeneous or non-homogeneous, we know how to do it as long as A, B, and C are constants. We know, but generally speaking, we do not know how to solve second order differential equations with non-constant coefficients. And actually there is no general method, but there is a beautiful trick that very often is helpful, and actually a lot of theory of so-called special functions arise from considering such differential equations. Let me explain how it works on a specific example, and that's going to be enough for you to have some vague but general understanding of this subject. Right, so we are going to look for the solution in the form of a power series. Well, but then we can differentiate this power series term by term. And so that's the first derivative. And we should multiply it by 3, right? So since here we have 3ty prime, we should multiply it by 3 and then multiply by t. Further, if this is y prime, then we should differentiate it one more time, and then we get y double prime. But then this series, and this series, we just put them together, and well, the ODE requires that the sum should be 0, so we just write down that we're going to get a 0 series, so which means that the coefficient at every t to the n is 0. So it's just as simple as that. So we have this 3 power series, and then we look at the coefficient at t to the n, and then we just require it to be 0. Well, but then we just, when we write it down, what we get is a formula that relates an and an plus 2. But now notice that if, say, I assign any specific values to a0, for example, -7, and a1, for example, 32, whatever, any specific numbers, then a2 is going to be a2 is obtained as an plus 2, where n is 0. So this is going to be minus n is 0, so 1 over 0 plus 1 times 0 plus 2 over 2, and a0 is -7. So -7 over 2 times 2, so this is 3.5. Then a3 is going to be minus, then 1. So a3 is what? a3 is n plus 2, where n is 1. So then n is 1, so here the numerator is 3 times 1 plus 1 is 3, divided by 1 plus 1, 2, times 1 plus 2, 3, times a1, 32. Well, you can calculate, this is minus, 16? And so on. So then you can calculate a4, a5, and so on. So what we construct this way is a formula for the solution. It is not a closed form solution, but it is not really much worse because we get a formula as a power series. Alright, one more thing. Sturm-Liouville theory. Sturm-Liouville theory is a bit strange at first hand. So it looks like this. So it is a second order differential equation of a very specific form. And usually we are interested in its boundary value problem, not the initial value problem that we've been concerned throughout our course, but boundary value problem. And Sturm-Liouville problem is to find real numbers lambda for which the boundary value problem has a non-trivial solution. Just to give you a bit of context, it is not strangely artificial, although it may seem that way, but it actually comes from some physics, from optimization, from solving Euler-Lagrange equations to some path integrals. Also, it is related to the theory of partial differential equations. So I'm not sure if you ever need it, go to our textbook section 11.2. One more little thing is that how do we calculate solutions of a differential equation approximately on a computer. So in this course, I gave you some idea of the so-called Euler's method. But there is a whole section in the textbook about numerical methods. So if you are keen, you can just say, as a part of your project work, instead of using a ready function for solving a differential equation, you can program one of those methods, for example, improved Euler's method or Runge-Kutras method by yourself. It is not very hard, so don't worry. So, for example, implementing the improved Euler's method would probably take like 15 minutes of your time. Well, reading what it is will take another hour, but it's not really a very difficult task. So if you're interested, if you are thinking of going into applied mathematics, you should